Hello everyone, I am Pushkar Kumar, Assistant Professor SRM CM Lucknow. So in the previous lecture we discussed about the various design philosophies that is going to use for designing of reinforced concrete structure. The various design philosophies we discussed are working stress method, limit state method and ultimate load design. In today's lecture we are going to discuss one of the design philosophies which is working stress method, that how we basically use that how we basically use the working stress method for the designing of rectangular singly reinforced section. So in this lecture we are going to cover different assumptions or working stress method and what are the different permissible values which are going to take for concrete and steel in this design philosophy, and what are the different sections, and then a numerical question for the related to analysis of this method. So the first thing is the different assumptions or say the rules of related to this design philosophies. This is also mentioned in IS code 456 2000 of annexure B of IS code 456 2000. Okay. The first very important assumption which we will take, that a section which is plane before bending remains plane after bending. It means let us take a cross section in which the width of the cross section is b and the total depth of the cross section is d, that there is a neutral axis which actually differentiate the tension zone and compressive zone if we applied a uniformly distributed load on this simply supported beam. So the upper part is basically the compressive zone and the part below the neutral axis is basically the tension zone. So the first very important assumption was that a section which is plane before bending remains plane after bending. So basically it means that the strain is basically increases as we go far distance from the neutral axis. Like we can see from the strain diagram, as we go far from the neutral axis, the value of the strain increases proportionally. Okay. The second very important assumption in this working stress method is bond between steel and concrete is perfect within elastic limit of steel. Okay. So within elastic limit of steel, the bond between steel and concrete remains is perfect, means they they share equally strain value. Okay. Now the third important assumption is that, like you can see from this cross section, that there is concrete below the tensile zone also. So the very important third important assumption, that the tensile strength of concrete is ignored, means the concrete will not share any tensile kind of strength below the neutral axis. The fourth very most important assumption is concrete is elastic, means the stress is in concrete varies linearly from the zero at the neutral axis to a maximum at the extreme fiber. You can see from this figure that the stress is directly increasing from the neutral axis to the maximum, to its maximum value as we go further to its extreme fiber. Okay. So at extreme fiber the stresses in concrete is basically find that is equal to sigma CBC. What is sigma CBC? We will discuss it is further. Okay. So the next assumption is that steel area is assumed to be concentrated at the centroid of the steel. Like you can see that the steel section is basically concentrated and the stress in this steel is basically concentrated at the centroid of the steel, that is T. Okay. The stress is sigma ST, that is basically at the centroid of the steel. Okay. And the last assumption which is taken in this method, that the modular ratio has a value equal to 280 upon sigma CBC, where sigma CB is basically permissible compressive stress in bending in Newton per mm square. Basically the modular ratio is defined as the ratio of the modulus of elasticity of steel to modulus of elasticity of concrete, means M is basically equals to Es upon Ec, that is modulus Ec. Okay. is EC, means modulus of elasticity of steel and the ratio of modulus of elasticity of concrete basically gives the modular ratio, but the working stress, but IS code basically refer that the modular ratio is not taken equal to ES by EC, basically it is taken equal to 280 upon sigma 280 upon 3 sigma CBC. Sorry, here 3 is basically missing, 280 upon 3 sigma CBC. Okay. So, why this value is taken? Because it incorporates the creep effect. So, this value does not involve the creep effect value, this value involves the incorporating actually the effect of creep. Okay. So, this is the we already discussed, this is the cross section of a reinforced concrete structure, this is steel, this is the width of the beam and this is total depth. Now, the most one important term, that is this is D, which is basically called effective depth. Effective depth. What is effective depth? Is basically when we remove, this is basically called the distance from the centroid of the steel to the extreme fiber is basically known as effective cover, which is provided, and the distance from the last point of the steel to the last extreme fiber is basically called clear cover. Clear cover. Okay. So, when we subtract the value of effective cover from capital D, means total depth of the cross section of the reinforced concrete structure, then we got the value of small d, which is also known as effective depth. Okay. So, we can we already discussed this strain curve and stress curve from the assumption. So, now what is the permissible stresses which are going to take in concrete while it is in tension. So, it is also mentioned in clause B 2.1.1 of IS code 456/2000 that for different grades of concrete, as we discussed in previous lecture, the permissible tensile strength is this. Like for M10 grade of concrete, the permissible tensile strength is 1.2. Although it is basically mentioned that concrete will not take any type of tensile stress, but in general the concrete is always be present. So, it should not happen that there is any crack developed, because we know that concrete is very weak in tension and very strong in compression. If tensile strength exceeds this value, then there may be possibilities that there should be a crack generated on that place. Okay. So, this value is basically given so that the value of tensile stresses in concrete should not exceed these values for these different grades of concrete. Okay. Now, the permissible stress in concrete in compression, it is also mentioned in table 21 of IS code 456/2000. For the different grades of concrete, you can see the permissible stresses in compression. So, when the concrete structure is in compression, there are two types of loading is basically seen. First one is bending and the second one is direct. Bending is basically represented as sigma CBC and the direct stress is basically represented in sigma CC. So, for M10 grade, you can see that the bending value, that the bending stress is equal to 3 Newton per meter square. The permissible stresses in concrete in compression is basically equal to 3 Newton per mm square, while for direct stress its value is 2.5. Means you can see that the stress, permissible stress in direct is basically low when compared to the bending, because when you apply the direct force, then there is then it felt it basically become weak, more weak when we apply a direct stress. Okay. So, this value is basically low when compared to the bending. Okay. So, till now we have discussed the permissible stresses in concrete, in compression or in tensile. Now, we discuss the permissible stresses. What are the basically permissible stresses in steel? It is also mentioned in, it is taken from the table 22 of IS code 456/2000, that what are the permissible stresses in steel. So, for the different grades of steel up to different dia, like up to 20 mm dia bar, we can take the the permissible stresses in tension is basically equal to 140 Newton per mm square, and for 415 grade of steel up to 20 mm, this value equals to 230 Newton per mm square. These are also important values, but for your subject, for your subject reference, these two values are very much important. So remember this. Okay. Basically, generally, sometimes these basic values are also mentioned well when there is a in questions, but you can also, but you should also remember that these values. Okay. Now, the modular ratio is very an important term, which is basically used in during analysis of reinforced concrete structure in working stress method. Okay. So, you can see a section where a load P is applied. So, this load is basically bothered by both the concrete and steel. Okay. So, we can differentiate, we can basically write the load into stress into area of concrete and then stress in steel into area of steel. So, this is one section. From strain capability, you know that it is equal to ES, not EC is equal to EC. The strain in concrete is basically equal to the strain in steel. So, here you can find that Fs is basically equal to m into Fc. M is basically the modular ratio. We talked that it is basically the ratio of modulus of elasticity of steel upon modulus of elasticity of concrete. Okay. So, from first and second equation, when we put in this equation, so you can find that P is basically equals to stress in concrete into area of concrete plus stress in concrete into modular ratio into AST. Basically, from this equation we find that the area of steel can be also converted into equivalent area of concrete by multiplying the modular ratio to the area of steel. It is basically used when we go do the analysis part. Okay. In this analysis part, so at that time we are going to convert the area of steel into the area of concrete, so that the analysis will become easy for us. Okay. Now, how we do the actually analysis of singly reinforced section. So, first understand what is singly means. Singly reinforced section means. Singly reinforced section means, as we discussed earlier, that above neutral axis there is basically a compressive zone and below the neutral axis there is basically a tensile zone. So, when the steels are only placed in the tensile zone, then it is basically referred as singly reinforced section. And if we put steel on both tensile as well as compressive zone, then it will be a doubly reinforced section. We will discuss it further. Okay. So, now like previous, as we can convert the area of steel into equivalent to the area of concrete, so we multiplied it equal to the m. So, here the concrete is in dotted because we converted the concrete is of no strength in tensile zone. Okay. So, it is neglected, as we can see from the assumptions. Okay. And now the AST is basically area of steel is converted to the equivalent area of the concrete. Okay. So, we can analyze that the movement of the area of the compressive zone area. So, area of the compressive zone is basically equal to the B into XA. XA is basically tells about the position of the neutral axis, that what is actually the position of neutral axis. So, XA is basically the position of neutral axis. So, we can area of compressive zone is basically B into XA, and the movement at neutral axis will be XA by 2. It is from there to there. So, it will be B into XA by 2. Now, the area of steel, which is equivalent to concrete, MAST into then movement at D minus XA, because from there to concrete it is basically equal to the effective depth, which is equals to D. So, this total value is equal to D, this is XA, then this value is equal to D minus XA. From this is a very important equation which is actually used for finding the position of neutral axis in different type of section. So, note it down. Okay. Now, what are the different type of section we see in working stress method design? Okay, methods. Okay, the first type of section we actually seen is the balanced type of section. What is a balanced type of section? Basically, say if a member is so proportioned that the maximum stresses in both the concrete and the reinforcing steel reaches their permissible values at the same time, then the section is termed as balanced section. It means the maximum permissible value which is in concrete and the maximum permissible stress in concrete as well as the maximum permissible stress in steel, both the values are reaching their its maximum limit at the same time, then you can say that this is a balanced type of section. And then the position of the neutral axis of this section, of the balanced section, is basically referred as critical neutral axis. That's why it is represented at xc, that is c represents basically the critical. Okay. So, from the this is basically the stress diagram. You can see the stress diagram previously, that there is a stress diagram in only in the compressive zone. Here is only a line like which represent the stress in steel, but here we convert the stress in steel equivalent to the concrete section. So, that is why it is divided by m. Okay. So, this is the stress diagram. So, from the stress diagram we can analyze the extreme value at the concrete fiber is equal to sigma CBC, while the extreme stress in steel is basically equal to sigma ST, and the position of neutral axis is equal to the critical neutral axis. So, and now from stress diagram we can actually assume sigma CB upon XC and sigma ST upon m divided by d minus XC. Okay. So, you can find from here that the position of critical neutral axis by this equation. This whole will be written as k, a factor basically to which is used to calculate the position of neutral axis. Okay. In balance section only. Okay. In balance section we are talking about here about balance section. Okay. Now, the next type of section is basically under reinforced section. If you find that there is a lesser amount of steel than compressive strength of concrete, if you can see that there is a lesser steel, means the permissible stresses in steel are maximum permissible stresses in steel are generated first than the maximum permissible stress generated in concrete, then this type of basically section is basically called under reinforced section. It means that the stresses, maximum stresses which is generated in steel equal to sigma ST, but the maximum permissible stress is still not generated at the extreme fiber of concrete equal to sigma CBC. It is basically less than sigma CBC. That type of section is basically termed as under reinforced section. Okay. So, generally the benefit of this type of section design is that in this the maximum permissible limit reaches in steel first, that it means the steel at its maximum permissible limit, okay, maximum stress limit. So, it will fail further if we applied load further. Okay. So, you know that the steel is a ductile in nature. So, its failure means that the failure is in ductile nature, means it gives a proper indication, proper warning before failing. That is why we actually prefer to design under reinforced section, that if any kind of failure is seen, then it will be seen in reinforced concrete section, that is ductile, means you get at least warning before its failure. So, generally we try to design an under reinforced section. And about the position of neutral axis, like you can see from the balance section, the position and compared to the under reinforced section, the position of neutral axis is basically less than above than the critical neutral axis. It means the position of neutral axis should be less then it will be a under reinforced section. It is also used for analysis or finding an under reinforced section. Okay. So, when you find a position of neutral axis which is less than the critical neutral axis, then it will be termed as under reinforced section, and the failure of this type of section is in actually tension failure, which is very preferable. Okay. The next very important section is over reinforced section, means when the stresses in permissible stresses in concrete reaches first its limit value, than the if we compare the maximum permissible limit maximum permissible limit in tension, means the concrete is going to failure. Okay. So, this type of section is basically mentioned as over reinforced section. So, here the maximum permissible limit first reaches in concrete, means the maximum permissible limit is equal to sigma CBC, but the stresses in steel still not reached its maximum permissible value, means the stresses in steel is still less than sigma ST. So, here you can find the position of neutral axis is below the critical neutral axis, means position of neutral axis is basically lower than the critical neutral axis. But in this type of failure, in this type of section, you actually see that the permissible limit reaches in concrete first, So the concrete will fail if any kind of loading exceeds. Okay, so this type of section is basically concrete is a brittle in nature. So in this type of section we generally see a compression failure or say brittle failure, means concrete will fail first before the steel fails. Okay, so we generally try to avoid this to design this type of section, because let's assume if you design this type of section, if it fails, then the concrete fails first and it will be dangerous for the people who is living under that concrete structure. That's why we are actually try to avoid to design this type of over reinforced section. So how to recognize that this is an over reinforced section? That when the position of neutral axis basically exceeds the value of critical neutral axis. Okay. Now the moment of resistance of section is an important term which is basically used to calculate the resistance of the concrete structure. Okay. So how we find it that? So first there is a cross section whose width is b and the total depth is d and effective depth is small d, and the area of steel, the total steel is equal to AST. So this is the strain diagram, and now this is the stress diagram, we have seen it further. Now the calculation of moment of resistance, you actually know that the moment of resistance is basically equal to the force into a distance. So here is the distance basically there are two forces, two type of stresses acting. First one is the compressive stress, the stress which is acting in concrete compressive zone, and the second stress which is acting on the steel. So this is the tension force which is calculated by stresses into the area of steel. Okay, stresses sigma st into the area of steel AST, and the second important the stress which is compressive force which is in the zone of concrete, which is equal to the half sigma CBC into x into b. See, it is calculated by taking the area of the triangle, or you can say taking an average like 0 plus sigma CBC divided by 2 into x. Okay. So you can calculate, and then the area, unit area into b into 1. So from this you can find the value of compressive force. So basically the line of action, the distance between the line of action of these forces denotes a value which is called basically lever arm. Okay, lever arm. Okay. Lever arm, that is lever arm is defined as z is equal to d minus x by 3, means this total distance is capital D, effective depth, and the compressive force will act at the centroid of this triangle which is at x by 3 from the top of the fiber, from top fiber. Okay. So total distance is d minus x by 3 basically gives you the lever arm. You can also write it d is equal to, just a second. You can also write z is equal to d minus k into d by 3. X is also can be written as k into the multiples of d. Okay, we have already seen it previously. Okay. Now d is can also written as 1 minus k by 3, and this whole term can be represented as j. Okay. So you can calculate the compressive forces. Now the moment, as we already discussed, that the moment of resistance is basically equal to the tension force or compression on any one of the force and equal to the lever arm. So for the balance section we can calculate any one of the we can take any one of the forces and multiply into the lever arm value. So we have already seen that sigma value is half sigma CBC into XC into B into J into D. So it can also be written as half sigma CBC, XC can be written as K into D, B into J into D, and equals to half into sigma CBC into K into J into BD square. So this whole term can be also represented as moment factor, which is Q. Okay. So we can calculate the moment of resistance is just by QBD square. Q is equal to half sigma CBC into K into Z. So this one is calculated by using the compressive force only. Now moment of resistance is also calculated by using the tension force into the lever arm. So tension force we already seen equal to sigma st into AST, and the lever arm is equal to d minus xc by 3. One thing need to be noted, that here we can using the value of position of neutral axis, the critical neutral axis we are actually using the value of critical neutral axis, because it is a balanced section. So we are using the critical value of critical neutral axis for calculating the moment of resistance for a balanced section. Okay. Now the second type of section we already discussed, that is which is under reinforced section. So under reinforced section we already seen the failure is basically in the steel. So we can take the moment of resistance from we can calculate the moment of resistance from tensile force into lever arm. So sigma st into a st into d minus xa by 3. Here you should note that the position of neutral axis is calculated not equals to critical neutral axis. Okay. We have to calculate, we already discussed, by equivalent the area of the compressive zone and taking the moment at the neutral axis, we can calculate the position of neutral axis, actual neutral axis. Okay. So from this formula we can calculate the moment of resistance in under reinforced section. We can also calculate the moment of resistance in with the value of compressive force, but we try to avoid because the value of Ca, basically the compressive force is not equal to sigma CBC. So we have to calculate from the stress diagram. So one more equation is added for the calculation, means the calculation increases. So that's why we actually prefer this equation for the calculation of moment of resistance in under reinforced section. Likewise, for the over reinforced section, we earlier see that the failure is in compressive with compressive force, means the concrete is going to fail in this type of section. So for this type of moment of resistance, we use the compressive force and lever arm for the calculation of moment of resistance, and try to avoid the use of tensile force and lever arm. But we can also calculate by using this tensile force and lever arm, but we have to find out this Ta, which is not equal to sigma st, because it is going to fail in compressive forces, means it is going to fail in concrete. So we are and the stresses coming in tensile will be less than sigma st. So we have to calculate this Ta value, then we can use this formula for the calculation of moment of resistance in over reinforced section. Okay. So from this equation is basically derived from the stress diagram you can see from the previous slides. Okay. So till now we have already found that how we calculate, how we decide that a section, which type of section it is, and also how to calculate the moment of resistance in different type of section. Further analysis or numerical questions we will discuss in the next lecture. Okay. Thank you.